Welcome to GTC 2021. Again, I think everybody coming to you from our homes. I'm sorry we can't be together in person, but excited to share what we've been up to at Rendered.ai. My name is Nathan Kundtz. I'm the CEO of Rendered.ai, and recently we've been taking the work that we've been doing in synthetic data and turning it into a common application framework that we think can be useful across the industry. So today I'm excited to share a little bit about that. Really the goal here is to share what we've been up to, and we're doing this because it's something we hope is going to be helpful across the industry, and we want your feedback. We'd like what we're building to be useful to those working with synthetic data or who are working in artificial intelligence and running into data challenges. In order to do that, I'll share a little bit of background on what synthetic data is and why it's important. And then get into why we think there's really a gap and a need for an application framework around synthetic data. I'll be talking about the framework that we're building and what's in it, how you can integrate applications with it, and then get to some demonstrations. And we'll wrap up with a brief discussion of how you can get involved. All right, so without further ado, let's get into it. So synthetic data has a really basic premise. The performance of artificial intelligence fundamentally depends on data. Typically, that data is a static asset, or essentially static asset in machine learning engineering framework. So sometimes, we will try to adjust the data, pick specific examples, maybe do data augmentation. But synthetic data is about really applying physics principles to be able to engineer our data. So be able to decide specifically what it is we want included and not included, and be able to use that to train models, to validate models, and to use turn the data into a flexible tool when it comes to model creation. So why do we care about synthetic data? It's really pretty simple. The fundamental performance of artificial intelligence depends on data. Now, typically we treat that like a static asset, and we're asking, maybe what kinds of augmentations we can do to the data. Maybe we're trying to be selective about what data we're going to use for training, but it's not something that we have a great deal of control over. And what synthetic data is about, especially in the context of computer vision, is using physics-based simulators to turn data generation into part of the engineering process. So something we really can control in the design process of AI algorithms. And so what we've been doing is not just thinking about how do we do these simulations or how do we do data set generation, but what does it take to turn that into an engineering process? What does that take to really build a workflow that allows you to improve and explain what you're getting out of the data generation process? So why might you want to do that? Well, let's start with sort of the obvious. A lot of the times, the most important things to see or identify or correctly understand are things we just don't see very often. It's edge cases, it's the overturned cars in the road, or strange phenomenon that pop up every once in a while, and we really need to be able to understand what's going on when those things happen, but they just don't present very often in data sets if you do a statistical sampling of the real world, and sometimes they don't show up at all. Another reason synthetic data can be really important is that it's often difficult to label data appropriately. So in computer vision with kind of RGB imagery from a camera, a human can often look at images and draw boxes around things and label them. And that works as long as it's not too blurry. A human brain does a pretty good job of understanding what's in there. But as you start to push towards the edge of the signal to noise in an image, or if you're working with a different type of sensor like radar, that might not be possible at all. And even when it is possible, data labeling is often not only very expensive, but is one of the most prone, one of the steps of the process that's most prone to error. But one of my favorites here is cold start problems. And if you step back and you think about what we're doing with AI-enabled sensing, just about every sensor that we use was really built without an AI pipeline in mind. And so what we have to do is we take that sensor that was designed to have performance levels that made sense for a human, we build a data set, and then we post hoc generate an algorithm. Well, in the future, that just doesn't make any sense. We're going to have to be able to build sensors so that they are able to perform well in a machine vision context. But in order to understand that, you've really got to build the algorithm and the sensor in parallel. And you just can't do that using classical single or few shot simulation techniques. We really need to move into the world of synthetic data, where you have large ensembles of data generation, and we can analyze the performance of sensors in the context of the algorithms that we can create. And then finally, it is often the case that the data sets that do exist, even if they're not uncommon, there's no labeling problems, and it's an old sensor, a lot of important data is restricted. And two great examples are security restrictions or medical and restrictions with, medical records with PII restrictions. Okay, so this is why we like synthetic data, but let's talk a little bit about how. How do we get there? Now, before we talk about how you get there, let's talk about how you don't get there. So it's really easy to fall into a trap in which you believe that if we've got good simulators, we'll naturally end up with a good and productive data set, and that will lead to a great AI model. This isn't flawed thinking, it's just a little bit naive because it misses a lot of what is really important in that data set. It doesn't touch on the things that we know from real world data sets are crucial, like the diversity of the data set or how well the simulator matches the domain of the real world. And so what we find in the real world is that, first of all, it's not that simple. In order to generate that data set, a lot of additional steps needed to take place. And secondly, it's really important to have that in an iterative context. So as we generate data sets, we want to be able to do that in a hypothesis-driven way where we can test our hypotheses, build new use the magic of television here, and then quickly get feedback and understand what improvements or not have been made. And it's only going through that iterative process that we end up with improved and explainable outcomes. So in order to do that, you need tools. You need to be able to manage your configurations, your compute, your data sets. I won't want to read this whole slide to you, but there are a lot of things that end up being required as you put that process together. And so when we talk about a common application framework, we're really talking about taking those things which otherwise you have to build every single time you're addressing a new simulation phenomena and putting it into a framework where we can access those in a common way. So let's talk a little bit about why you might want to run iterations. And here I want to talk a little bit about one of the most common failure modes for synthetic data, which is domain mismatch. So anytime we simulate a data set, it's never going to be perfect. No simulator captures all of the physics and diversity of the real world. And you can think back to, say, old rendering engines from the early 2000s or late 90s. You could see just from your eye that the images didn't look very realistic. And that's still largely the case today. When you look at, say, the CGI sort of video game imagery that can be used for synthetic data, your
Alright,
human
so our
brain
download
knows
is
immediately
complete, and we can take
that
a look
that's
at what is
not
actually
real.
sitting inside there.
Now, in order to quantify what this means in the context of artificial intelligence, we've got to find some way to reduce the complexity of that information. And one way to do that is by doing what's called a latent space projection. And this presentation is not intended to get into the details of this, but suffice it to say that we can, through a number of different mechanisms, we can take sophisticated data sets, very high dimensional data sets like imagery, and we can ask how they would project meaningfully on a two-dimensional or three-dimensional scatter plot. And what you'd find is that if you had a real data set and a synthetic data set, you'd see groupings like this. So when you first start, for instance, you might see a small overlap between the real data and the synthetic data. And if you naively trained on the synthetic data, you wouldn't get very good performance. There are some examples of the real data where you might see good performance, but there's a big chunk here that wouldn't be covered by your data set. So how do we go about fixing that problem? Well, there's no one answer. There's actually a bunch of things we can do. One obvious one is we could try to just improve the fidelity of our simulation, improve the sensor modeling. We can use new techniques in image transfer, like style transfer or GAN-based techniques, to try to learn that underlying structure and then use the simulation as the ground truth and map it into the appropriate domain. And that can work. Has some limitations. In general, you can result in improved accuracy, but you're also still going to be limited to the environment right around the real data set that you might already have. So what are some alternatives? Well, you can work on domain expansion instead. If, for instance, your limits in fidelity were really about your understanding of the parameters from the sensor, you can vary those parameters. And then we can start to play with modifiers on our objects, sometimes even non-realistic objects and backgrounds, and different types of noise, which can either be applied post hoc to images or throughout the simulation process. Now, if you get too carried away with this, your accuracy can drop because your domain here can expand too large. But at the same time, you'll end up with a result that's less sensitive to the specific environment and less sensitive to the region of real data that you might already have. So the point here isn't that there's one answer, it's actually exactly the opposite. This is a trade-off that needs to be made as part of the data generation process. And so it's not about giving you the magic tool, it's about giving you the variety of tools needed to get to the answer you need for your applications. But here's the kicker. It's really not practical to build up that capability for every single use case out there for synthetic data. There's just too many applications, there's too many ground truths, and every single one of those has a myriad of different sensors which are used for them. So there are times where maybe there's enough overlap that you can go deep, but for a lot of these are long tail applications. And while a lot of money has gone into investing into these simulation codes in these environments, getting from there to productive synthetic data requires these additional tools, and it, in our opinion, just doesn't make sense to rebuild all of that infrastructure for every single application. So, our solution is to provide a framework to address these things. And really what we want to be able to do is abstract away the elements of synthetic data that are application specific. So we take those and we turn that into an application, and it plugs into a platform which provides the compute management and execution framework, that configuration management we talked about before, a deep learning sandbox, a lot of the different things that are necessary to make this effective. And we do that in a way that allows users to access both the data creation and the data they've generated in a flexible way, and provides mechanisms for sharing content so that the next time you generate additional channels, you're not having to recreate as much of the same content. Okay, so in order to do that, we have to have some form of universal configuration management, or what we call universal simulation architecture. What we provide is this node-based flow, and we like this approach because it does seem to be the best practice in computer graphics and in other circumstances in which heavy diversity generation is important. This allows us to flexibly stack modifiers, introduce different objects, introduce different agents and agent factories into a simulation in a way that's very intuitive. And once we have that universal configuration, we can figure out how we're going to interface to it. Our approach is to define a common interface between a Docker container and these tools. And so what we actually do is we provide utilities that allow us to take that simulation code, Dockerize it, and then place it in a format that easily plugs in to all of these tools necessary for moving into synthetic data. So not just the configuration management, but the things necessary for collaboration and library management and high performance compute. We like the Docker framework. Obviously, it's sort of the standard way to go about deploying any sort of large compute environment. It allows for easy scale. But we do need to structure that interface well, and so we provide some additional utilities to make sure that the Docker container can obey the interface rules into the Common Application Framework. And we've been at this for a while, so we've got quite a few examples of this working, going across a wide variety of different types of physics and different types of synthetic data at this point, whether that be RGB imagery and cameras, infrared, far infrared, or thermal infrared, or midwave and shortwave infrared, some medical imagery, Earth observation, satellite Earth observation, synthetic aperture radar, and now actually getting into X-ray physics. And so we're excited by this because we're really seeing that this approach, this common approach, can be used to address problems across this incredibly diverse space of applications, and gives us confidence that we'll be able to address a wide part of the synthetic data market needs. In fact, we've just started to bring on our first third party. So thus far, we have been building applications within this framework and using that to satisfy our clients' needs. And our first third-party application provider is Quadradox. They are experts in X-ray simulation, incredibly detailed and accurate physics-based simulation of X-rays, useful, of course, in baggage scanning, but also in medical applications and food safety. Very excited for this partnership and to really help propel Quadradox's business and bring them and their tools to customers that otherwise wouldn't be able to get access to this kind of high fidelity data. All right, so let's pause here and we will start actually walking through the tool and give you a sense of how it works. Okay, so here we are. We're going to be logging in. And when we log in, we are presented with a workspace. This is actually a collaborative environment in which we can work with others to build data sets, define different configurations, and try them out. You can see the different configurations in this workspace are down here along the left. We can see jobs that we've run and some that are actually ongoing right now on the tool. And then we can also take a look at some of the examples of data sets over here. So for instance, if we click up here, we can start to browse through this particular data set. And what we find is that this sort of visual indication of what's in these data sets is incredibly useful. The first time that you generate a synthetic data set, you're very likely to remember what it is you asked for in that data set. The second time, yeah, you remember pretty well, but by the fifth iteration or 10th iteration, it becomes a little bit difficult to just remember. And while we do provide a great depth of metadata, and you can interrogate that to know what was actually done to produce these images, often just looking at a few of them is incredibly helpful. But let's take a look at one of these graphs. This is a relatively simple one. It's actually about as simple as it gets. And in it, we're doing some overhead imagery simulation. We have a construction area. We're going to place some cranes in it and aim the sensor. So let's see what happens when we click the preview button. So now we've actually taken this graph, pushed it to the back end, and it's going to do a single job for us. And this is helpful just to say, like, is that what I wanted, or would I like to see something else? Now, if we wanted to do something else, we can come over here, and this is where the various nodes are. And we can do things like add additional objects. You can see there's a pretty extensive library available here. We could do things like add modifiers. You know, what if we cared about cranes that had snow on them? Well, that's pretty easy to do. Just go like that. And actually now, because we have both paths, we'll have both some cranes with no snow and some cranes with some snow coverage on them. Now, we can continue to do this, and typically you would until you've defined what you want in that scene. And there's a lot of ability to not just change what you're looking for in as seen, but drive statistically what's happening with any of the modifiable parameters. And that's why that preview button becomes in handy, because as you build this up, we've found it's really helpful to just get a sense quickly of what is happening in that scene, and is it what we expected. Once you've built that up, you're likely to have something that looks a little bit more, say, like this. So a lot of different content here in green, a lot of different modifiers, really leveraging different distributions, statistical distributions of various parameters, so that we get a lot of diversity in our data sets. All right, once we're happy with the configuration, we compile it to the back end. Now we say compile, and I'll be frank with you, all we're really doing is taking this and exporting it in a YAML file. And the reason that you should care is that if we want to, we can actually go ahead and download that right here. And that becomes editable in a text-based mode as well, and you can upload that yourselves either right here or through API. But if we're happy with it, we can come over to jobs, and we can see that that graph that we just published is sitting here ready to be turned into data. And all that we have to do now is, well, sometimes it's helpful to give some description of the data set you're planning to create, give a priority level so that you can manage it relative to other resources that are maybe being used, and then press Run Job. Now what is actually happening is, as we speak, we're spinning up instances, EC2 instances, to start chugging away producing those simulations. So that's going to take some time to spin those up and begin going. So let's go forward, and we can look at our library. So here's where we collect data sets. We can view the different properties. Here are some nice examples of unrealistic backgrounds, something which can be particularly helpful with synthetic data. So a great example of what I mentioned earlier around how you might introduce noise that isn't the same kind of noise that you can introduce post hoc. You can actually do these non-realistic noise features. We can look at, here's an example of one that's closer to that test that I showed you earlier, cranes in different background configurations. And let's say we wanted to download one of these in order to train an algorithm on. Well, you can access this data directly where it resides on an S3 volume, or we can actually just download it here. Now it's downloading. You can see it's about a gig, and it'll start running. So there we go. It's plugging away. All right, so our download is completed, and we can take a look at what's sitting inside there. So first of all, our images are all, here we go, nicely packed away. But you'll notice a few other things. You'll notice that we have annotations sitting here in a COCO format. And then we can also pull out masks. So these are actually segmentation masks in ping format of the different objects if you want that. And we can interrogate the metadata of each of these scenes as well. And so we can actually look and get a lot of detailed information about what each of the objects in the scene have done. So you can see here we're placing cranes. Each of them has been modified to extend arms and rotate in different ways. So for instance, if we later wanted to figure out if maybe we were only having trouble detecting cranes when the arms were fully extended, that data is actually available to you in this great depth of ground truth information that comes along with this. Just a couple other things that you get. So this is actually the YAML file that defines the graph that we compiled. And so if, for instance, you had a data set and this was the graph that generated, you can always upload this back to generate more data. If for some reason you wanted to use it in a different workspace or modify it somewhat and generate new data, this allows you to actually take a look at that directly. And then, of course, we just have some high-level metadata associated with this data set. So I hope that gives you a sense of how we can go from something that's really very general in terms of a universal simulation framework and produce a common application framework that we could really leverage across a wide variety of different tools. All right, well, thanks for hanging out with me. I really enjoyed sharing a little bit about what we've been up to. I hope you find that intriguing. And for some of you, if you're interested, of course, we'd love to hear more from you. We'd love to hear anything you have to tell us, but in particular, if you're working with synthetic data or think you might be interested in working with synthetic data, we'd love to know what kinds of things you need most. Is it different analytics tools? Is it more efficient compute? Different simulation modules? What can we do to make sure that our platform is really serving you effectively? It's great for us to know that now. We're still very much in the build and design phase, and so the more information we can get from the community, the better. Now, if you happen to have simulation tools and are looking for ways to get that to market or take them and really extend them so that they can be more effective as synthetic data tools, we'd love to hear from you as well. It's early right now, but we are allowing a limited number of third-party suppliers onto our platform. We'll do a lot more of that in the future, I promise, but in the short term, if this is something that you think could be useful, just please let us know. All right, thanks again, and take care. I look forward to hearing your questions.